All right, so now that we have talked about rotational kinetic energy, more specifically, rotational conservation of energy, let's now do a couple examples and see how this actually works. So, first example, we're going to consider case number one that we talked about last time, which is we're going to have the pulley, but the pulley is not going to be moving translationally up and down, side to side. It's only going to be sitting still while this thing is actually just rotating. So this is going to be case number one. So in this problem, we're then going to consider, here's our pulley. Pulley then has a radius of 0.3 meters, a mass of 4.8 kilograms. Then attached over that is then a mass M1, which is at 35 kilograms, M2 at 38 kilograms, and then M2 is going to go down while M1 is going up, and it's going to go down by a distance of 2.5 meters, while M1 goes up by a distance of 2.1 meters. And we want to know then is how fast is M1 and M2 going by the time it reaches, in this case, the bottom, and this one reaches the top. Now we're going to do this two ways. So in part A, we want to consider what happens with ignoring that rotation of the pulley, and then in part B, we're going to take that rotation pulley into account. Now, this is just your typical Atwood machine. So we've seen this before, but doing part A, but let's just do it again just for fun. Okay, so we're going to use conservation of energy to do this. Now, in part A, we can ignore the rotation of the pulley, so the size of the pulley and everything doesn't matter. Again, we're pretending it's massless and frictionless, so this thing is just going to be there but not actually contribute to anything. Now, we talked about before, since we have two objects which are moving, we then combine both of those objects into the same expression for conservation of energy. In this case, the only thing which has potential energy is gravitational. There is no spring present, so we only have conservation of energy involving potential energy. So in this case, we're saying the change in kinetic energy of mass 1 plus the change in kinetic energy of mass 2 plus the change in gravitational potential of mass 1, change in gravitational potential of mass 2, all equal to the work done by the non-conservative force. Now, in this case, since this is frictionless, we don't care about any friction forces. We're also going to pretend this is in a vacuum, so we have no air resistance. So in this case, we have zero work done by a non-conservative force. Again, we talked about this in class before, but again, technically, if I was only looking at M1, there is a non-conservative force. In this case, it's an additive non-conservative force via the tension. In this case, there is a non-conservative force, which is a dissipative non-conservative force via the tension again, because this thing wants to fall at the rate of g, but the tension in the string here is keeping it from doing so, and this one just wants to sit still, but is being dragged up, which is why it's additive. But, again, if I consider both of these into the same expression, those two works, this tension work and this tension work, are equal and opposite, therefore they just cancel out. Right? Now, the other thing we know is by the time this guy reaches down here, its velocity downward, v, is going to be the same thing as this guy's velocity v up in this direction. So these two v's aren't independent, they're exactly the same. Now, if I take, for example, this line down here, as my y is equal to 0 location, that means that this one starts off with 0 gravitational potential, but ends with non-zero. This one starts off with non-zero, but then ends with 0, which means the change of potential energy for him is negative, while the change of potential energy for him is positive. But in both cases, the change in kinetic energies are positive because they start off with 0 but end up with non-zero. So good. So remember, change is always finite minus the initial, so this is 1/2 m1 v squared minus the initial, which is 0, plus 1/2 m2 v squared minus the initial, which is 0, plus the final gravitational potential for m1, which is just going to be m1gh minus the initial, which is equal to 0, plus the final gravitational potential for m2, which is 0, because it's going to finish at the bottom, minus the initial, which is mgh, is all then equal to 0. Now again, since those two velocities are the same, we can factor that out. Those two GHs are the same, but since we're looking for the velocity, let's bring that term to the other side. So we can rewrite this as 1/2 m1 plus m2 times velocity squared is equal to g times h times m2 minus m1. Again, this one becomes positive when I bring it to the other side, this one becomes negative. Good. So now let's solve this guy for the velocity. So finally we get that the velocity is equal to the square root of 2gh times the ratio then of the masses. So again, m2 minus m1 divided by m1 plus m2. So, substitute and plug in my numbers. What I find in this case then is that the final velocity is 1.42 meters per second. So that's how fast M2 is moving downward by the time it reaches the bottom of H, and that's how fast M1 is moving upward when it moves up by distance at H. Now, before we do part 2, or part B, let's talk about first our expectations. So our expectation should be that what? How should the velocity now in case 2 or case B compare to the velocity of case 1? So, what do I mean by that? What I mean by that is by the time this thing falls down a distance of H and this one moves up a distance of H, should it be moving faster, slower, or the same when I'm now considering that this guy is actually rotating? Well, let's think about it. In this case, what we know is that what? What's happening here is I'm having a change in potential energy in this guy going in then to this guy changing potential energy and kinetic energy into each one of these guys. Which means that this initial potential energy must be deviated into 2 objects. Those 2 objects are basically the kinetic energy and the change in potential energy for this guy. Now, if this guy is rotating, that then is going to cause that initial potential energy here to now be diverted not just into the kinetic energies for these guys and the potential energy of this guy, but also into the kinetic energy of this guy. Meaning that it takes energy to cause this guy to start to rotate. Which means that that energy, that initial energy which is stored here, has to be diverted now into 3 things as opposed to just 2 things. Which means that this final velocity here should be moving slower than it was in this case when I take the rotation and pulling into account, because I have to divert energy into causing this guy to rotate. Which means that some of that energy, which is stored in that gravitational potential energy, is now diverted into its rotation, which means that it has to be moving at a slower rate. So our expectation should be that the final velocity is less than this velocity of 1.2 or 1.42 meters per second. Now, the other thing is, when it comes to change in potential energy, I mentioned this in the last video, what's happening is the pulley is only doing this. So even though this point down here is moving from here up to here, but the center of mass is what is important. Now what's happening is for the pulley, the center of mass is not moving up or down or moving left or right, most importantly up or down, which means that its potential energy always is fixed. It's always the same. So what I care about is only that location of the center of mass. Since this thing is only rotating about, the center of mass of the pulley itself never changes, which means its final potential energy is equal to its initial potential energy, which means the change in potential energy is 0. So that means when I go to do part B, let me erase all this up for stuff. What that means then is the only thing I have to add then is the change in potential energy, or the change in kinetic energy of the pulley itself, not of the gravitational potential energy, because that's just going to be 0. I mean, I could write it if I want to, but then that's just going to give me simply 0. So let's go ahead and do that. So the only thing that's going to be different is now I have to add on the rotational kinetic energy of the pulley itself. Now in this case, since the pulley is rotating about its center of mass, the only thing I care about is the moment of inertia about the center of mass. We'll talk about what that is in a second. So the only thing that's going to change here then is I'm going to have a final rotational kinetic energy, which is 1/2 the moment of inertia about the center of mass times the angular velocity squared, minus the initial, plus 1/2 m1v squared minus the initial, plus 1/2 m2v squared minus the initial, plus m1gh minus the initial, plus 0 minus m2gh equals 0. So the only modification right now that has occurred is this extra term, just from the rotational kinetic energy of the pulley. Now, we also talked about this in the video, but basically, what has to be true is that what? The tangential velocity of this outside portion here and here must match that exactly of the linear velocity of the masses. Which means that if this thing is moving with a velocity v, then this point here has to have a tangential velocity also equal to that same velocity v. Same thing here. So this point on the extreme must also have a linear velocity, even though this thing is moving with an angular velocity. So the tangential velocity here and tangential velocity here must match the linear velocity here and here. Otherwise, what's happening is that the string, or whatever's attaching these guys together, is slipping. But just like we kind of talked about before, we're going to consider is that this string is not slipping, and it has purely static friction, which is causing this thing to rotate. So ultimately what that means then is that this angular velocity here is not independent of these two linear velocities. It's actually dependent on them. So what I care about is the fact that this tangential velocity of this point must then be equal to the radius of my pulley times then its angular velocity. Which means that the angular velocity is equal to the tangential velocity divided by the radius. But again, this tangential velocity must be exactly the same as this linear velocity of the mass itself. Now, I'm going to use that into here. So this is now going to become, so this velocity is going to be the same as this one, going to be the same as this one. Well, let's do it in steps. So I'm going to 1/2 times 1/3 inertia about the center of mass times v squared divided by r squared plus m1 plus m2 plus m1 v squared plus m2 v squared is all then equal to g times h times m2 minus m1. Right-hand side stays the same from last time. Now, since I want that v squared, I can move the r squared to underneath the moment of inertia about the center of mass, and then factor out v squared, so this is going to become 1/2 times the moment of inertia about the center of mass divided by the radius squared, plus m1 plus m2, all times velocity squared, is simply equal to gh times m2 minus m1. Now, if I solve this then for the velocity, I don't need this anymore, so let's get rid of this. So this finally gives me then that velocity, then it's going to be twice of g times h times m2 minus m1. So same thing as before, except now I'm going to get an m1 plus m2 plus moment of inertia divided by the radius squared, all square root. Now, structurally, what we can see is that indeed this will be less than the other one. And we can see that because now what's happening is that this denominator is becoming bigger by this extra factor. And if I take something and I divide by a bigger denominator, what that means then is that this thing is going to get smaller. So all this means then is I have to know what is the center of mass, or what is the moment of inertia about the center of mass. Well, this thing, in our case, we're going to pretend that this is a solid disk. Turns out that a solid disk is something more like this, that the moment of inertia about a solid disk is then 1/2 times its mass times its radius squared. So here we have the moment of inertia about the center of mass is equal to 1/2 the mass of the pulley times the radius of the pulley squared. So in this case, this r squared is going to cancel out that r squared, which means it actually doesn't depend on the radius of this pulley. It only depends on the mass of the pulley. So it's going to be the same thing as 2 times g times h times m2 minus m1 divided by m1 plus m2 plus 1/2 the mass of the pulley, all going to d squared root 2. Plug in my numbers. What I find in this case then is that the final velocity is 1.4 meters per second. So what we find is that, yes, in part B, the final velocity is indeed less than it was in part A, because again, what's happening is I have to divert that initial gravitational potential energy that M2 had on this side into now causing this thing to rotate, and M1 and M2 to move. And also give some of that gravitational potential energy into the gravitational potential energy of M1. But now I'm going to have to divert it into more things. Again, basically 3 different kinetic energies at this stage, plus 1 gravitational potential energy. I now have to give up part of that kinetic energy that I got before, which causes the whole entire system to move slower. So indeed, our expectation was met in this case, so it should actually be moving slower. So let's do one more example. So the next example we're going to look at is for case 2. Or case 2, again, is we're going to be looking at an object which is not only rotating, but it's translating at the same time. So let's look at that rolling without slipping we talked about. So again, rolling without slipping just means that this guy is going to be here, and this thing is going to move translationally and rotating with an angular velocity. But again, what we saw last time was that here, the kinetic energy, or the total kinetic energy, just simply diverts or splits up into simply this plus this. So here, we're going to consider this situation. So let's say I'm now going to put a track on here. So here's my track. So here's my track. And what I want to consider is, let's take two objects with the same size. So if I put these two on top of each other, the radii are exactly the same, have roughly the same amount of mass. They are different materials, but in this case, it turns out it doesn't matter. And we'll talk about why that is in a second. And what I want to do is put these two both simultaneously on the track and then race them to the bottom. And what I want to know is which one of these guys will have the bigger velocity by the time it reaches the bottom of the track. I.e., when these things get to the bottom of the track, which one is faster? Is this going to end up something like this? Or is it going to end up something like this? This is what we want to know. Now, first things first, what we want to talk about is here, why, first of all, is this thing going to rotate? So what I want to consider is that this thing is rolling down, but it's also rotating as it is rolling down. Now, if I wax this thing, what's going to happen in that case, if I really, really wax it, these things are just going to slide down, act like point masses, and they're going to have exactly the same amount of velocity at the bottom. So that should be our first key thing. So if I wax it, what I'm doing is I'm taking away friction. So if I have no friction, these things aren't going to rotate. They're simply going to slide down. In that case, there's no difference between the two of them. And as we know from conservation of energy, it doesn't even depend on the mass of these guys. They're simply going to have the same velocity by the time it reaches the bottom, which only depends on the height at which these things go down. That's it. Now, but what's going to cause these guys to rotate is friction. Right? So again, if I didn't wax these things, these guys are going to rotate, and as they rotate, that rotation is going to be caused by friction. Now, what that means is now we have friction in the problem, which means that when we write down our conservation of energy, so let's start off with our conservation of energy, we know we have the change in kinetic energy, which is going to be about the center of mass, which is our rotational kinetic energy, plus the change in our translational kinetic energy of the center of mass, plus the change in gravitational potential, since there's no spring in this case, again, is equal to the work done by the non-conservative force. Now, since we have friction, does that mean we have a non-conservative force? Well, let's think about what type of friction that this is. So what we're going to be considering is that this thing is rolling without slipping. So again, all that means is I'm going to take this guy and roll it down, but it's not going to slip. So it would be slipping, what it would do is it would go translationally, slowly rotate as it is translationally going. That's going to be rolling with slipping. Which means in this case, if it was doing this, slowly catching and rotating every once in a while, that would be a kinetic friction. And indeed, in that case, we would have a work done by non-conservative force. But in this case, we want to consider this, which means that it's rolling without slipping, which means that there is no motion of the object relative to the surface, which means it has to be a static friction. Now, this static friction is very important, meaning that it is actually not a non-conservative force. This static friction is purely causing this object to rotate. That's it. It's not taking energy away from the system. What it is doing is it's acting as a catalyst to cause this thing to divert some of its translational kinetic energy into rotational kinetic energy, meaning it's causing a change of energy from translational kinetic into rotational kinetic. It is the work which is being done to cause this thing to rotate and change from one type of energy to another, but it is not a non-conservative force because it's not actually taking energy away from the system. It is purely there to cause it to change from one type of energy to another type of energy. So, what this means then is as I consider this thing, we actually have zero work done by a non-conservative force. This is going to be 0, again, because we're assuming this is vacuum, so I have no air resistance taking energy away from the system. So now we establish that, what that means then is since this is a particular type of friction, which is static friction, which is going to cause these guys to rotate, since that doesn't take energy away from the system, I don't have to care about the fact that it is a maximum static friction or not. I just don't care. Which means that, again, this thing should be independent of the mass. The only thing it should depend on is the height at which it's going down and something else. So, now, let's think in our minds. I know I can't have you guys vote like I would usually do in class, but let's think about it. So which one do you think is going to win? Would it be the disc, the solid disc, or would it be the hoop? Let's find out. And then we'll talk about why this happens. So I'm going to print these on top, start them off at exactly the same time, and let's watch the bottom and see which one is actually going to win. Nice. So clearly, the winner was the solid disc. Okay? So why was it the solid disc? Well, let's do the math and let's find out. So this is our example. So here, let's say that's what the height change is going to be from where it starts up here to where it finishes down on the bottom of this table. So we're simply going to call that H. Let me draw the picture over here. So here's our schematic. So now here, what I care about is the height change from the center of mass, which means that this is actually the height at which I care about. But again, by the time this thing reaches the bottom, the center of mass is going to be here, which means the actual height change is going to be this height H, which is exactly the same height from the top of the incline here to the table in this case. Because again, what happens is what I care about is where that center of mass is changing. So initially it is at this height here, but then by the time it reaches the bottom here, it is now this high above the ground, which means that that change of height is exactly the same as the height difference between the top of this plane to the table itself. So let's call that to be H. And again, what we want to know is how fast is the center of mass velocity of this thing as it's moving in this direction by the time it reaches the bottom. Now, let's take in this case that the initial velocity is equal to 0. So the initial velocity, which means that the initial angular velocity is also equal to 0. So good. So let's put that together. So this becomes 1/2 the moment of inertia about the center of mass times the final angular velocity squared minus the initial, which is 0, plus 1/2 times the mass of the object, so we're going to call that m. So let's say this has a mass of m. Times then the velocity squared minus the initial, which is 0, plus the gravitational potential, which is simply mgh, minus the final, which again is equal to 0. Let me get this out of the way so we can actually see. Good, slide this guy back. So good. Now again, what's happening here is as this thing is rotating about, this thing has an angular velocity going in this direction, but again, this tangential velocity here, which is pointing down in this direction, has to be moving with exactly the same amount of velocity as the center of mass, which again means that if this thing has a radius of, say, little r, then that center of mass velocity is simply equal to the radius times the angular velocity. So just like in the last problem, the angular velocity of this thing is not independent of the center of mass velocity. It's actually related to it via the radius. So that means I can rewrite this then as 1/2 the moment of inertia about the center of mass times the center of mass velocity squared divided by the radius of the object squared plus 1/2 the mass of the object times center of mass velocity squared. Should be final, which is 0, minus the initial, which is mgh, minus then mgh is then all equal to 0. So again, what we want to do is solve this for the center of mass velocity. So let's factor that out. So this becomes 1/2 the moment of inertia about the center of mass divided by the radius squared plus the mass of the object times the center of mass velocity squared is equal to mgh. So finally, we get the center of mass velocity is equal to the square root of 2 mgh divided by the mass of the object plus the center of mass moment of inertia divided by the radius squared. Now, what's the difference between these two objects? Well, it turns out that if I look up the moment of inertia about the center of mass of pretty much any object, it turns out that the moment of inertia about the center of mass is proportional to the mass of the object times the radius of the object squared. So for most of these things, it's going to be written as c, where c is some constant times mr squared. So c in this case is simply equal to a constant. So let's substitute that in here. So in this case, what happens is I put that in here, the r squareds are going to cancel. This m will be the same as this m, which is the same as this m, which means all the m's are going to cancel. So at the end of the day, this is going to become 2g times h divided by 1 plus c, all of that square rooted. So what this means then is what? If I want to know which one of these guys is going to win, what that means is all I need to know is what is that factor of proportionality in the moment of inertia. Now what this also says is if I want this quantity to be as big as possible, what I want then in this case is for the denominator to be as small as possible. So this tells me then that what? The one with the smallest moment of inertia is going to be moving the fastest by the time it reaches the bottom. So put that in some context. What I have then is that what? The moment of inertia of the disk about the center of mass is equal to 1/2 m times the radius squared. And then the moment of inertia of the hoop is equal to simply its mass times its radius squared. Now, what that means is that this one has a smaller moment of inertia than this one does by a factor of 1/2. So that means if I look at this structure, c for the disk is simply 1/2, where c for the hoop is equal to 1. So 1/2 is smaller than 1, which means that this guy, which has the smallest one, is going to win, which in this case is the solid disk. So we didn't see that this one actually made it to the bottom faster, at least had a faster velocity by the time it reached the bottom, as opposed to this one. And the reason for that is, again, this one has a smaller moment of inertia than this one. Now, does that make sense? Well, yes. Now, again, remember that moment of inertia is basically the equivalent of mass, which means it's a resistance for this guy to rotate, as opposed to mass, which is an resistance to that to be becoming accelerated. So it's much easier for me to cause this guy to rotate as opposed to this guy to rotate, which means I have to divert even more energy into this to try to get it to rotate, as opposed to this one, I don't have to divert as much energy into it to actually get it to rotate. So that means if I'm putting less energy into the rotation of this one, the translational energy, since in both cases, all I'm doing is changing from gravitational potential into kinetic energy, I have to divert then less into rotational, which I can divert more into translational, which allows it to go faster. So again, since this thing has a smaller moment of inertia, it takes less for me to actually cause this guy to rotate as opposed to this guy.